All right, so here we are tackling the rational review portion of our midterm. So first we are simplifying expressions. So looking at this first one, the only way I can reduce is if I see a factor on top and a factor on bottom that match, because that simplifies to be just one. So I'm going to go ahead and rewrite what's on top in standard form, negative x plus 5 over x minus 5. And then I can divide out that GCF on top of negative 1. Leaves behind an x minus 5. And now I see a factor on top and on bottom that match, which reduces 1 to 1. So my final answer here is just negative 1. Okay, over here I see a monomial over a monomial, right? There's no pluses or minuses in between my number and my variable. So here I need to look at the numbers and see if I can reduce, and then the variables to see if I can reduce. So for the numbers, the 35 and the negative 14, both divisible by 7, so I get 5 over negative 2. And then the x's cancel away 1 to 1. So that's it. I'd say negative 5 over 2. If you want to tell me a negative 2.5, great, I'll take that too. Okay, this one is different because on top I have a binomial over a monomial. So I need to factor down the top to see if I have anything that I can cancel away. So if I look at my GCF for these two terms, they're both divisible by 35 and by x. So 35x times, in parentheses, 2x squared minus 1 all over 10x squared. All right, so looking to see if there's anything I can cancel, I see that the 35 and the 10, both divisible by 5. So I'd have a 7 here and a 2 here. I have an x to the first power, x to the second power. So here I would bring that down, right? Subtract that 1 down, and I'd see that I have x here canceled away over just x on the bottom. So it's like 1 over x. All right, that looks like that's all I can do. So you can leave it as 7 times 2x squared minus 1 all over 2x, right? That's fine. Leave it factored, no problem. Or distribute out the 7. We'll take it as 14x squared minus 7 over 2x as well. Both of those formats are fine. Okay, next up here, we see a monomial over a monomial. So the first thing that I think to resolve are all of those negative exponents. I'm just going to draw attention to all of them just to see clearly. I'm going to move them to the other side and make them positive. So let me draw out a big fraction bar. First, if I look at that negative 32 and the 24, they are both divisible by 8. So I see a negative 4 over 3. Now, that x to the negative 9th is going to come down, be positive, and there's an x to the first that it's already next to, right? So they're going to be packaged together in just a moment. Okay, that y to the negative third is going to come up. That y to the 0 is just 1. Okay, and then for the z's, I have a z to the 6th that's already here, and z to the 4th that's going to come up right beside it. So the last thing to do is to consolidate the y's, the z's, and the x's. So I should end up with negative 4 y to the 3rd, z to the 10th, all over 3x to the 10th. All right, next skill, we're looking at the domain of each expression in interval form. So whenever we're looking at a fraction, a quotient, we can't have 0 on the bottom of a fraction. So my first thought is to factor it. So usually I just factor all of it, but the numerator part really doesn't impact my domain. So here, even if I factor the top and I get x minus 8 times x plus 4, the domain restriction comes from the bottom, and that's x minus 4 times x plus 4. So even though when I factor it and I can see that these would cancel away, my domain restriction comes from how the problem started. And I know that here x, when x is 4, that would make this part 0, would make the whole bottom 0. So really it cannot be 4. And then same thing over here. If x is -4, that would make this part 0, which would make the whole thing 0. So it can't be -4 as well. Again, the domain restriction comes from how the problem started. I can't have any value for x that makes the bottom go to 0. That makes it undefined. Now, as we've learned how to graph these as functions, we know that this part would cancel out, which means that this would present as a vertical asymptote, and this would present as a hole. Again, both restrictions on the domain. So when I write this in interval notation, I'd say, well, x can be anything from -∞ to -4, union -4 to 4, union 4 to infinity. Right? It's our way of saying, well, x can be anything, just not exactly -4 or +4. All right, the next one here, we see kind of a double whammy. We see that we have a root on the bottom. So that tells me 2 issues that I'm going to have to resolve. So first thing that I'm going to see here is that I know that the radicand part, that 4 minus 3x, the root, what's underneath the root, the radicand, that number has to always be greater than or equal to 0. So I have 4 minus 3x has to be greater than or equal to 0. So take away the 4. So -3x greater than or equal to -4. Divide by -3. I got to flip my inequality because I just divided by a negative. X has to be less than or equal to 4/3. Okay, so first thing is that my radicand, right, the number underneath the root has to be something that is greater than or equal to 0. So right now, x has to be less than or equal to 4/3 for that to be true. I also know that my denominator, right, the root 4 minus 3x, that has to not be equal to 0. So here it can't be 0. I usually start by just making it equal to 0 and then I negate it. So here, if I get rid of the square root, it's squared both sides, and I'm still at 4 minus 3x equals 0. Okay, so then from here, as I solve, I take away the 4. -3x would equal -4. Divide by -3, and x would equal 4/3. Right? So it can't equal 4/3, or else the entire bottom would be equal to 0, and it would be undefined. So the 2 things that I have to tackle, the fact that there is a root on the bottom, my radicand has to be greater than or equal to 0, and at the same time, I'm solving for the exact value of x that makes the bottom equal to 0. So these are here, this is saying this is the spread of values that x can be, but it also cannot be exactly 4/3. So if I write this as interval notation, I'd say from -∞ to 4/3, parenthesis on the 4/3, because it cannot be exactly 4/3 on the bottom. All right, next we have a series of just operations. So adding, subtracting, multiplying, dividing. So the first one up here, it's telling us we have to multiply here, these 2 parts, and then divide by this part. So let's make sure we factor this and see what we can cancel. And then in order to process this last part, if I'm dividing this, I'm really going to multiply by its reciprocal. All right, so I'm going to start by, again, just factoring everything that I can. Can't do anything with the 8x squared over x minus 4. That's already done. But over here, I have a difference of cubes. That's x cubed. That is 4 cubed. So I have x minus 4 times x squared 4x, 4 squared is 16. Follow the SOAP, same sign, opposite sign, always positive. And then I have a 6x right here. And then it's going to be times, because I'm going to take the reciprocal, x plus 4 over x squared plus 4x plus 16. Okay, look what I did there, right? I tried to make it easier for you to simplify, because I see that these trinomials can now cancel away 1 to 1. Let's see over here, we can cancel away the x minus 4's 1 to 1 as well. Okay, here I have the 8 and the 6, both even. So 4, 3, like that. And then I have the x squared over x. So I'll have an x here and a 1 here. That's all I can do. So on top, I would have 4x times x plus 4 all over 3. Or I can multiply it out and say 4x squared plus 16x over 3. Either way is fine. Okay, next one here, we are subtracting. And to subtract, we need a common denominator. So I need to look at, what is this denominator here, the trinomial? What does that factor into? That factors into x minus 3 times x plus 2. I'm just going to cross it out so I can see it factored. So that means that over here I need to multiply by x minus 3 over itself to have that common denominator. And this x plus 4 that's in the numerator position, that is a package. So I need to see it that way before I move into the next step. I'm going to start by resolving my numerator, because here I'm going to have to FOIL out the x minus 4 and the x minus 3. So the first, the outer, the inner, and the last. So right now I have a negative 7x plus 21 minus parentheses x squared. I'm going to have a minus 3x minus 4x. So minus 7x plus 12. But keep in mind, I'm subtracting that package. That's why I have parentheses here. I'm going to keep working on the numerator. I know that the denominator is really x minus 3, x plus 2, but I'm going to add that back in just a moment. All right, so distribute that negative. We have negative 7x plus 21 minus x squared plus 7x minus 12. Okay, here, combine the like terms. So I have negative x squared, done. Those 7x's, right, they're opposite, so those cancel away, and then just plus 9. Now I'll put that denominator back in, the x minus 3, x plus 2. Okay, so now I'm looking to see if I can factor so that I can reduce anything down. I can divide out that negative 1 times x squared minus 9, right? It's going to be a difference of 2 squares. And then x minus 3, x plus 2 on the bottom. All right, that difference of 2 squares here will factor. So I have negative 1 times x minus 3 times x plus 3 over x minus 3 times x plus 2. Okay, good. I have something to work with. These x minus 3's will reduce down, right, 1 to 1, and I'm left with negative 1 times x plus 3 over x plus 2. Or if I distribute back out, negative x minus 3 over x plus 2. Again, we'll take it either way. All right, next up. So in this one here, I have a binomial on top, and I actually have a binomial on the bottom. What makes this one sneaky is that I see that I have negative exponent on the y and on the x, but they're joined by addition, right? It's not a monomial. These are two separate terms. So my first step is going to write it as x plus y on top over 1 over y plus 1 over x on the bottom. That helps me see it a little bit more clearly. So now I can see that my common denominator, my LCM, would be x times y, right? Because here's the fractions I have. The only thing I see are x and y. So if I want to clear my fractions, I'm going to multiply by xy over xy. Now, on top, if I distribute that out, I'm really just going to have to factor it later. So I'm just going to kind of leave it right here for a moment as xy times x plus y on top. But when I distribute this on the bottom, if I take 1 over y times xy, the y's cancel out and just give me x. And if I multiply the xy over 1 over x, those x's cancel away and just leave me a y. And then look what we have. We see the x plus y over the x plus y, which will cancel away 1 to 1. And my final answer is just xy. Easy peasy. Okay, next up, here a more complex fraction, right? Fractions inside of fractions. Here's the big fraction bar where we see 2 separate pieces on top, and then here we see this guy on the bottom. So if I look at all of the denominators that we have, this one has an x, this one has an x minus 1. This one, if I factor it, would be 3 times x minus 1. So I know that I'm going to need a 3, I'm going to need an x, and an x minus 1 as my least common denominator. So here I'm going to write that out, 3x times x minus 1 over itself. Okay, so then I'm looking at the top. I'm going to block this out for a moment, and I'm distributing this over those 2 terms. So first I have 4 times 3x times x minus 1 over x. So the only thing that would cancel here would be the x's. So now here I would have 12 times x minus 1. Okay, and then over here it's going to be a minus. Now here I see that I'm multiplying 5 times 3x times x minus 1 over x minus 1. Those x minus 1s will cancel away, so it's really just minus 15x. Okay, all over on the bottom. So here, let me just cross that off so I can see it factored, right? This is like saying it's over 1. So here it's like this is the numerator, this is the denominator. So the 3's cancel away, the x plus 1's cancel away. I just have x. All right, so this is what I need to resolve now. I'm going to distribute the 12. So I have 12x minus 12 minus 15x all over x. Okay, next step, I have a negative 3x minus 12 over x. Okay, divide out the GCF of negative 3. So I have negative 3 times x plus 4 over x. And there's nothing that I can reduce. So I can leave it like that, no problem, or multiply it back into standard form, which is the negative 3x minus 12 over x. Again, would take it either way, no problem. Okay, last up in E, here I'm adding, and I see that I have y minus x and then x minus y in the bottom, right? So if I want to first just flip one of them around, maybe I do this one here, flip it around into negative x plus y. Right now it looks like that. And if I divide out the negative 1, now I can see that those denominators are so close. What I need to make them the same so that I can add these 2 separate fractions is give this one a negative 1 over negative 1. Okay, so now once I do that, on top I'll have y minus x, and on bottom I have a negative 1 times x minus y. Okay, let me whip this around to negative x plus y. over -1 times x minus y. Okay, divide out a -1 on top, leaves behind an x minus y, really over itself. So what happens here, we can see that the -1 over itself is 1 to 1. The x minus y over itself is also 1 to 1. So this one resolves to be just 1 as our final answer. All right, flip it over to the back. All right, here practice with finding the inverse. So we know that with an inverse, we first just switch our x and y values. So I have x equals 2 over y plus 3 minus 7. Okay, I'm going to add the 7 to the other side. So x plus 7 equals 2 over y plus 3. Okay, I'm trying to solve for y, so I need to clear it out of the denominator position. So I'm going to multiply each side of the equation by y plus 3. Make sure that I see this as two separate packages on the left. So I'm going to add those parentheses. I have y plus 3 times x plus 7, all equal to 2. Okay, divide out that x plus 7 from both sides. So now y plus 3 equals 2 over x plus 7, and then I just have to take away 3. And I've done my job. So my inverse function ends up being, inverse of function h is 2 over x plus 7, take away 3. Okay, next I'm taking this function here, this rational function, and I want to rewrite it so that I can see all the transformations. So that really only works when I have something linear over something linear. So here it's going to first be x minus 6 here. I'm trying to divide that out of the negative 2x plus 5. Okay, I like my structure, so I'm going to build my parentheses 2 terms wide and get my subtraction there ready to go. And I'm thinking of, well, how many times does x go into negative 2x? Or x times what is negative 2x? And that'd be negative 2. Okay, and then multiply it back, and we get negative 2x plus 12. Okay, next step, negative 2x minus a negative 2x is 0. So 5 minus 12 is negative 7. That's my remainder. So right now I have g of x is equal to, divided out, negative 2 times plus that remainder of negative 7 over x minus 6. And when I write it to see all my transformations, I would just whip it around and say negative 7 over x minus 6 and then take away 2. And then I can see that there would have been a vertical flip, vertical stretch of 7, 6 right, 2 down if I was to go ahead and graph it. All right, next, if we give you words, can you build the function? So here in 6, I'm saying it's a rational function. It has a vertical asymptote at x equals 5, horizontal asymptote at y equals 3, and a hole when x equals negative 1. Write the simplest equation that could represent this function and find the location of the hole. Okay, so let's start with f of x equals big fraction bar. Okay, so a vertical asymptote at x equals 5. So I must have a factor of x minus 5 on the bottom that I can't have on top, right? Because if I did, that would present as a hole and not an asymptote. Okay, I have a horizontal asymptote at y equals 3, so there must be a 3 over 1, right? And it has to be the same degree in order to produce that asymptote. Now, in fairness, it could have been like a 6 and a 2 or a 9 and a 3, but the leading coefficients would have to reduce to a value of 3 to have it at y equals 3. So I'm going to keep it simple. Keep it 3 and 1, but note to self that it needs to be the same degree. So right now it is linear on the bottom, So I would need something linear on the top. But I have one more piece of information, that there's a hole where x equals -1. So that means that I must have x plus 1 on the bottom and on top. So now I have something linear over something quadratic. It's not the same degree, and I need it to be the same degree in order to get that horizontal asymptote at y equals 3. So the easiest thing I can add is just simply an x, but it could have been like x minus 12 or x plus 4, and I'd still get these three pieces of information. What I need is same degree to produce that horizontal asymptote at y equals 3. So now it's quadratic over quadratic. This looks good. I'm going to leave my function just like this. And box it, of course. Okay, then I'm saying, well, where would the hole be? So if this reduced, right, these would cancel out. So I would have y equals 3 times -1 over -1 minus 5. So I'd have a -3 over a -6, which would be 1/2, right? Y would be 1/2. So my hole would be at -1, 1/2. All right, second one here. Rational function, we have an x-intercept at 4, 0, a vertical asymptote at x equals -6, and a hole when x equals 2. So same instruction. Let me just flesh out f of x equals big fraction bar. Okay, so if I need an x-intercept at 4, 0, then on top I must have a factor of x minus 4 that doesn't cancel away. So that factor on top produces the x-intercept. Okay, we have a vertical asymptote at x equals -6. So must have an x plus 6 on the bottom that doesn't cancel away. And then a hole at x equals 2, I'd have an x minus 2 over itself, because again, it must cancel away. So if I read this back, right, there's my hole, there's my vertical asymptote. That factor on top would give me the x-intercept. Okay, great. I have it. We're all good. Simplest form. So here I'm just going to transfer that down into this space. So my function f is x minus 4 times x minus 2 over x plus 6 times x minus 2. Okay, and if I actually look for the hole, I'm going to look at it in its reduced format and plug in the 2. So y would equal 2 minus 4 over 2 plus 6. So -2 over 8 becomes -1/4. So my hole would be at 2 comma -1/4. All right, 2 more problems and we're done. So here, can we find the perimeter of the isosceles triangle? So the perimeter means add up all the sides. And since these two are the same, I could start by saying that my perimeter is 2 sides that are both c over c plus 9 plus 27 c minus 9 over c squared plus 4c minus 45. All right, so this is really an addition of rationals. That's my problem. So right now I know that I have 2c over c plus 9 plus 27c minus 9 over c squared plus 4c minus 45. Okay, and I want to factor that just to see what it's going to become. So that will be c plus 9 times c minus 5. Okay, I'm going to look at it factored just like that. So on the left, I can see that to get a common denominator, this is going to need a c minus 5 over itself. Okay, so my next step is to consolidate all of those numerators. Let me distribute the 2c over the c minus 5. So I have 2c squared minus 10c. And then over here, I have 27c minus 9. Let me go ahead and clean that up before I put the denominator back in. So I have 2c squared plus 17c minus 9 all over c minus 5 times c plus 9. All right, I'm hopeful that I can cancel more, so I have to see if I can factor out this trinomial on top. So if I can, I know it's going to be a 2c right there with a c here, okay? And then I know that the numbers here and here have to be 1 and 9 or 3 and 3. I know that in the middle I need a 17c. That comes from the outer and the inner. So if I put, say I put a 9 here, right, I see that that's going to be 18c and a 1c. Now that will work if I put the plus here and the minus here, because I'll have 18c minus 1c. There's my 17c in the middle. And then here's my c minus 5 times c plus 9, which I love because that lets me reduce this part down and leave my answer at 2c minus 1 over c minus 5. That is all I can simplify. Slide that up. All right, last one. We're looking at a right rectangular prism. I'm going to zoom out a smidge. All right, so volume is given. We want to find the width of the prism. So we want to find this little guy right there. Okay, we know that the length and the height are marked. All right, so we should know that our volume, right, is base area times height for any right prism. Our base is a rectangle, so just length times width, that's our base area times the height. So if I want to solve for the width, I can divide each side by the length and the height. And I see that my width is just the volume divided by the length times the height. All right, so if I write that out, I know that my volume is the x minus 1 over 12x. And I really just want to divide that by the package, the product of x squared minus 1 over 6x cubed plus 30x squared, okay, times x squared plus 11x plus 30 over x squared plus 7x plus 6. All right, so let me slide that up a little bit. Okay, now I just have to factor everything down. So I have x minus 1 over 12x. Okay, and then here I'm going to still have it just divided by. And then I'm just going to factor all of this out. So here's a difference of two squares, x minus 1, x plus 1. Here I have a GCF of 6x squared, leaves behind x plus 5. Okay, over here, that's going to factor to be x plus 6 times x plus 5. And then here, that'll be x plus 6 and x plus 1. Okay, so here if I clean this part up first, the x plus 6's cancel 1 to 1. The x plus 5's cancel 1 to 1. The x plus 1's cancel 1 to 1. So now it's really x minus 1 over 12x divided by x minus 1 over 6x squared. So I'm going to make that a multiplication problem. I'm going to say, well, that's x minus 1 over 12x times 6x squared over x minus 1. How lovely. Those x minus 1s, they cancel away. Okay, the 6 and the 12 becomes 1 and 2. And then the x squared over x gives me an x over 1. So final answer is just x over 2. All right, have a great day.